Hello warriors, this is Miss Lemons, and today I'm going to be going over the example calculation, or an example calculation that would model what you should do during your pre-lab, and then this can also be a guide as to what you should do during the actual lab calculations. So let's go ahead and get started. So number one says to calculate the molar mass of the hydrated salt. That's NiSO4 and 7 waters, all right, 7H2O. From the background section, it says, because the formula includes a definite ratio of anhydrous salt to water, you must include the molar mass of both the anhydrous salt and the waters when calculating the molar mass of the compound. So we know how to calculate the molar mass. We know that we just need to look at the periodic table and then look at the subscript numbers in each portion of this formula and multiply each element by their respective subscript number. So for NiSO4, I multiplied 16 by 4 because there are 4 oxygens. And so I get 154.76 grams per mole. For water, I end up getting 18.02 grams per mole, but I need to multiply that value by 7 because there are 7 waters in this hydrated salt formula. Once I do that, we know that a hydrated salt is comprised of an ionic compound and the waters. So we have to add both of these values together to get our final answer, which is 280.90 grams per mole of hydrate. Okay, so now that we've calculated the molar mass of the hydrate, we need to calculate moles of the anhydrous salt. Now, 77.5 grams, this is actually a value that you are given in number 2. But for when we do the lab, this is the value that you calculated by removing the amount, or what this is your ending product. Okay, so 77.5 grams is what we measured at the end of heating our sample. So that's the value you are going to be converting from grams to moles. So we know we're starting with 77.5 grams, and our conversion factor is 1 mole of X is equal to the molar mass of X in grams. And so we know that we need to be using this conversion factor in this fraction down below. So whatever unit's on top, what's on top must come down. So if we have grams of nickel sulfate on top, we need grams of nickel 2 sulfate on the bottom. So I'm going to put the molar mass of nickel 2 sulfate on the bottom. And then the, I did not round in this one. This is actually accurate. The top should be the 1 mole of nickel 2 sulfate. So then we go ahead and multiply across the top and across the bottom, divide the top and bottom, and we end up getting this ridiculous number. We're going to go ahead and round to 3 sig figs. So I have 0.501 moles of nickel 2 sulfate. Save that number for later. Then we're going to calculate the mass of water that has evaporated. This is pretty simple. We know that all hydrates are made up of an ionic compound with waters attached to it. We started the lab with a hydrate, right? Then we boiled off the waters. So what are we left with? An anhydrate. So there is no water left. So if we subtract the mass of the anhydrate, what we end the lab with, from the mass of the hydrate, which is what we started the lab with, we would end up with the mass of water, what's missing, right? What left the system and floated into the air as water vapor, okay? So we are actually given a value for the hydrate in the pre-lab, but in the actual lab, you are using the value, how many grams, between 2 and 3 grams, of hydrate that you measured out before we even really got the experiment started. Subtract the 2 and we end up getting 63.0 grams of H2O. Of course, then we're going to take that and convert 63 grams to moles. And again, this is what we just calculated on the previous question. So we're going to start with 63 grams, and we're using the conversion factor 1 mole of X is equal to the molar mass of X. So what's on top must come down. So if we have grams of water on top, we need grams of water on the bottom. This is the molar mass of water. And so if we use 1/2 of our conversion factor, we have to use the other half of our conversion factor on top. Multiply across the top and across the bottom, divide your top and bottom, and we end up getting 3.49611, which I'm going to round to 3 sig figs because we started with 3 sig figs. So you should have 3.50 moles of H2O. Okay, again, keep that number moles in your back pocket. Question 5 asks us to use the mole ratio to determine the final formula of the hydrate. Okay, so actually this is not unlike what we've done for empirical formulas in the past. If you need to use your empirical formula cheat sheet, go ahead, but I'm going to refresh your memory on what we're doing here. So instead of calculating or finding the lowest whole number ratio between atoms in a compound, like calculating the empirical formula of something, you're actually going to be calculating the lowest whole number ratio of compounds within the hydrated salt. But it functions the same way. It's still a mole ratio. You're using moles and you're comparing the amounts. So we calculated 0.510 moles of NiSO4 and 3.50 moles of H2O. Keep this in our back pocket. Remember, these are the values that we calculated in question number 2 and 4, and we will be using them for this question because we are trying to find the mole ratio between the salt and the water. So we need the moles for salt and moles for water to find the mole ratio. Okay, so wow, that just happened out of nowhere. So just like calculating an empirical formula, you are going to divide all the mole values by the smallest mole value that you have so you can get the lowest whole number ratio. Well, between these two, which number is smaller? 0.510 or 0.501 moles of NiSO4. So you're going to divide both of those values by 0.501. Now that's going to be nice because it's going to make NiSO4 equal 1. We need whole numbers. So let's go ahead and divide both of these by 0.501 moles of NiSO4. When we do that, we end up getting 1 mole of NiSO4 and then 6.986 blah, 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 blah. But it really should be very close to a whole number. So we're going to go ahead and just round it up to 7 because we can't have 6.9 waters. You can only have 7 full waters, right? We need a whole number ratio. So the ratio of water to salt is 7 moles of water for every 1 mole of nickel 2 sulfate. And remember, the same number of nickel 2 sulfate formula units always bond with the same number of H2O molecules when forming a hydrate. So this ratio is a definite proportion for that substance. All right, number 6 says, using your answer from question 5 and the information from the background section, write the chemical formula of the hydrate. So we calculated in the previous question that the ratio of water to salt is 7 moles of water to 1 mole of nickel 2 sulfate. We're going to use both of those values we discovered and plug them into our formula. Now we know that all hydrate formulas contain not only the ionic compound and the water, they also contain this dot. And that dot shows us that it is a hydrate and that these are 2 separate compounds that have been joined together as one substance. But they are separable, like we can separate them via evaporation or boiling. And if you look here, we also have our coefficient 7 in front of the H2O. Now, you might have noticed that we didn't write the 1 in front of nickel 2 sulfate. And the reason behind that is if there is no coefficient written, just like if there is no subscript written in a formula, we assume it is 1. And then this is actually a nice throwback to the previous unit. Now we're going to calculate the percent composition of water. Now remember, percent composition is a part of a whole. So if I asked you, what is the percent of points you got correct on your test, you would take the number of questions you got correct divided by the total number of questions on the test. Just like this, we are going to take the percent, or calculating the percent of the hydrate that is made up of water. So we're going to take just the mass of water and divide it by the mass of the total compound, which is the hydrate. So we have our value from question number 3, and that is the value we calculated by subtracting the hydrate and the anhydrate from the other way around, the anhydrate from the hydrate. And then 140.5, this is a given value in our pre-lab, but this is the value we measured at the very beginning of the lab. Divide the 2, multiply by 100, and we get 44.8. Let's go ahead and just keep this to 3 sig figs unless otherwise notified. So we're going to say 44.8% of this compound was made up of water. So that is all I have for you guys today. If you need additional help on these calculations, remember you can always reach out to your teachers or reach out to your lab partner.